Is it supposed to mean recording has started? They changed the message? Okay, that's confusing. Okay, so let us get started. So we started discussion of photon finally. And so the idea was to take the Lagrangian where all the derivatives are replaced by the covariant derivatives as we talked about before to ensure that it is gauge invariant. And on Wednesday, I showed the Lagrangian with charge 2e for the Cooper pairs, but now I changed it to just charge e because that's probably more generic anyway. And then in addition to this Lagrangian for the matter particles, we add the Lagrangian for the electromagnetic field, E squared minus V squared. And so that, of course, is how you can reproduce the Maxwell's equations once you actually take variation of this action with respect to scalar potential and a vector potential. And once you do so, you can identify what the charge density and the current density are from the matter part of the Lagrangian. So this is now a consequence of this Lagrangian, not an input. And this one is easy to understand. Phi appears in the matter part of Lagrangian only here. So if you take the variation with respect to phi, that will pull out E times psi dag of psi. That's exactly what this one is. So we already kind of knew that the number density is psi dag of psi, and therefore E times that must be the charge density. But this is now something that would just come out by taking the variational principle. So you don't need any additional input for this. In the same way, when you take variation with respect to vector potential that appears in this kinetic energy part of the Lagrangian, again, this is derived from the Lagrangian, and you find this expression. So this is the expression we actually used already when we talked about the superconductivity, but this is also generically true for any given charge of the matter particle. So this Lagrangian reproduces Maxwell's equation, and now we know how to quantize it. So that's the process we started on Wednesday, but I'd like to go a little bit more slowly. Okay. And so we do need to pay attention to the fact that there is a little complication we didn't have in the case of the Schrödinger field. We have this gauge invariance, and also the vector potential comes in 3 components rather than just 1 component. So we pay attention to these extra things as we go on. So anyway, so that's why we started. Do you have any questions about this? So the program we are now going through? Okay. So you've seen this canonical quantization already many times by now. So I hope you got sort of a more comfortable with this whole idea. And to deal with this gauge invariance, the easiest thing is to just pick a gauge. And it turns out the simplest gauge for this purpose is the Coulomb gauge, which I believe you have seen in electromagnetism, and that's what we're going to actually use. So divergence A, vanishing. And one sort of unfortunate fact about this though is that the Coulomb gauge is not Lorentz invariant. So if you go to a different reference frame, you first do the Lorentz transformation, then it doesn't satisfy the Coulomb gauge condition anymore. So you have to do a gauge transformation so that it satisfies the Coulomb gauge condition again in the new reference frame. So that's one little complication, which is there, unfortunately. But as long as you are in a particular frame, of course, you don't need to worry about this. So that's the attitude we take here. And once you take the Coulomb gauge, then the Gauss's law becomes simple because the electric field has a piece that goes like the A dot, but divergence of A dot is time derivative of divergence A, and therefore that vanishes. So that piece drops out. So divergence E just becomes Laplacian phi. And we know the solution to this just by solving the Poisson equation. So as a result, then we can write this Lagrangian for the electromagnetic field. And this is the expression you have seen on Wednesday. The piece I did not write is the piece associated with this scalar potential. So once you actually put this solution to the Poisson equation back into the Lagrangian, there's an additional term that looks like this, which I hope makes sense. Basically, this is the Coulomb energy between 2 charge densities at positions X and Y. And to avoid double counting, there's a factor of 1/2. So that's the additional term you get. But as you can see, this piece contains only dependencies on matter particles. and no dependence on the vector potential. So for the purpose of quantizing the vector potential, then this Coulomb potential term doesn't matter. So that's why I didn't write it on Wednesday, but some of you asked the question about it. That's why I added this back in to make sure that I didn't drop anything. But even if you do write everything out, again, for the purpose of quantizing vector potential, it doesn't matter whether you have this Coulomb potential or not. So that's why I didn't write it last time, but now I do write it, and still discussion remains the same. And having said that, so I just focus on the first two terms because of this, because the last term doesn't depend on vector potential. And then looking at this form of the Lagrangian, it basically just looks like A is what corresponds to X in harmonic oscillator. And once you go to momentum space, the derivative just becomes a number, a wave vector. So this piece corresponds to half m omega squared x squared. So A plays the role of X. And this is m over 2 x dot squared. So X dot or A dot plays the role of momentum, and A plays the role of the position of a harmonic oscillator. So that motivates you to write this mode expansion, where A, that plays the role of X for the harmonic oscillator, should be written as A plus A dagger using creationization operators. And A dot, that plays the role of momentum in harmonic oscillator, should be written as A minus A dagger times I to make sure it's Hermitian. So the difference between A and A dagger is A dot. Sum of A and A dagger should be A. So that's the inspiration from knowing the harmonic oscillator example. And this prefactor here is something I worked it out ahead of the time, anticipating how we can reproduce the correct normalization for the canonical commutation relation. So this is something we're going to verify on the next few slides. But anyway, so I hope this analogy makes sense. Once you identify vector potential as playing the role of the position operator in harmonic oscillator, it should be given by A plus A dagger for the creationization operator, and A dot plays the role of momentum, and therefore it should be written as A minus A dagger. So that's the idea of this mode expansion. And obviously, because vector potential has three components for X direction, Y direction, Z direction, so you have this mode expansion for each direction. So right now you see this creationization operator also has this index I representing three different components of the vector potential. Okay, let me pause here. I'm sure you got some questions. No? Everything clear? Okay. Then, so the one little notation I'm going to use is that P, of course, has the meaning of the momentum. And if you look at this exponential factor, P over H bar has a dimension of 1 over distance. That's the wave vector. And de Broglie's relation tells you that if you divide it by H bar, this becomes the momentum. And so this ends up being the momentum of each photon as an interpretation. And once you have a momentum P for the photon, then its size times C is the energy of the photon. So I'm going to use this notation EP. And I also use this notation of the angular frequency omega P, which is of course related by a factor of H bar, again, de Broglie's relation between angular frequency and the energy of a quantum particles. So we're going to use this notation. So the E being C times P is the input from relativity we are going to use for the later purposes. Okay, so canonical quantization by now should look familiar to you. The first thing you do is take the derivative of the Lagrangian with respect to the time derivative of the canonical variable. A is the variable, A dot is something you will look at and take the derivative with respect to it. A dot appears here, this is square of that, so that gives you factor of 2, that cancels this 1/2, therefore that ends up being epsilon naught, dielectric constant of the vacuum, times A dot. So this is the conjugate momentum to AI. So that tells us that this is the correct canonical commutation relations. AI, that's the variable, that corresponds to X, and epsilon naught AJ dot, that is what corresponds to momentum, so P, is IH bar. But now that this is a field that comes with the delta function, as we have seen already many times, and it has these three components, so they're independent variables. And for each I, you have the corresponding conjugate momentum, so you get this Kronecker delta. So commutation relation does not vanish only when I and J indices are the same. So that's the canonical commutation relation. And these prefactors are something I anticipated, but now we have to actually verify it by using these commutation relations between the annihilation creation operator. And annihilation creation operator now carries this momentum index. So this is the Kronecker delta for the momenta, and also carries the spatial index I and J. So that's the Kronecker delta for the spatial indices X, Y, and Z. So using this normalization of the creation annihilation operator, if you plug in this mode expansion into this canonical commutation relation, you can just work this out and can indeed verify that it turns out to be this IH bar delta IJ delta X minus Y. So using this prefactor, it correctly reproduces the canonical commutation relation among the field operators by using the correct normalization for annihilation creation operators. So that's the way you can now start building the Fock space or Hilbert space in general. Okay, any questions about this slide?
I have a question.
Go ahead.
I'm sort of confused about what exactly it means to operate, let's say, the first component creation operator. So are you creating a photon with like I guess I don't understand like how you create just one component.
How you create one component. Okay, so actually there is one issue we haven't talked about yet. So we are already talking about this multi-components here, but there is also an issue of Gaussian invariance, which I haven't addressed yet. And that comes on next slide. So hopefully after doing that, that becomes a little bit more transparent. So can I do it that way? Then I'll get back to your question, Chirag. Thank you for asking the question. So make sure that I don't forget it. Any other questions? Okay, so as Chirag asked already, so this issue with the multi-component is an important question because the way it looks like right now, there are three independent set of photons. But something I'm sure you have already learned in electromagnetism is that the photon has two polarizations. And right now we seem to have three, and that precisely has to do with the gauge choice I haven't discussed yet. So at this stage, A has all three components, but if you take divergence of A, it is supposed to be zero in a Coulomb gauge, but I don't see that over here. So there's still one more step we have to implement into the correct definition of creation annihilation operators, and that precisely, I hope, would answer the question Chirag was asking. So what are we supposed to do here? So we took Coulomb gauge. So we have to make sure that the Coulomb gauge condition is satisfied, but right now it doesn't look like it. So what you have to do then is to take divergence of A and make sure that vanishes. But when you take divergence of A, the X dependence appears only in this exponent. So you find the P is pulled down from the exponent. So you find PIAI plus PIAI minus PIAI dagger, because there's a minus sign here. On the other hand, divergence of A dot should also vanish because it's just a time derivative of the Coulomb gauge condition. And if you look at that, divergence here also pulls out P from the exponent. But in this case, this minus I and this minus sign add up. So from divergence A vanishing, you get a condition that PIAI minus PIAI dagger vanishing. But from the condition that divergence of A dot vanishing, you'll find PIAI plus PIAI dagger vanishing. So if you take linear combination of them, you'll find the condition that PIAI should vanish. And also PIAI dagger should vanish. So now we have to implement this additional condition coming from this Coulomb gauge condition. And what it means is that this AI annihilation operator has to be orthogonal to the momentum vector. And we know exactly how to actually implement this constraint. Namely that once you have a momentum vector, let's say it is pointing the z direction, then there are two orthogonal directions to it, namely x direction and y direction. So then this annihilation operator should have components only along x direction and y direction, but should not have component for the z direction. So that actually eliminates AZ in that case. And of course, P pointing z direction is a simple case where I can just throw away AZ. In general, you have to write the orthogonal vectors. So in general, you introduce this idea called the polarization vectors. So if P is pointing in an arbitrary direction, given by the spherical coordinates theta and phi, then there are two orthogonal vectors to it. And one of them can be written this way. And you can see if you multiply them together in inner product, the first two pieces would add up to sine cosine. Last piece is negative sine cosine, and they cancel. So you can see they are orthogonal to each other. And for the second vector over here, this is minus cosine phi sine phi. And the y component is sine phi cosine phi, they cancel. So once again, this vector is orthogonal to the momentum vector. So by writing this annihilation operator, which looks like it has three independent components, but given that we need to satisfy this Coulomb gauge condition, there are only two remaining components, and two remaining components can be written using these two polarization vectors. And for each polarization vector given by lambda, whether it's 1 or 2, I have an annihilation operator 1 or 2. So this is the way I now have only two sets of annihilation operators for a given momentum. And of course, correspondingly, again, two sets of creation operators for that same given momentum. So now this vector potential field is written in terms of creation operator and annihilation operator of a given polarization. And polarization vector is always orthogonal to the momentum vector because of the Coulomb gauge condition. Okay, so that's the supposed to be responding to Chirag's question. Let me see if he's happy.
Yeah.
Okay.
I'm happy.
Good, good, good. Any other questions? Okay, and as I believe you also have learned in the classical E&M, you can take this basis of the polarization vector for what is called the linear polarization, which corresponds to linear or transverse polarization vectors, which corresponds to this kind of wave. So if this is a direction where photon is moving, or if that's the classical electromagnetic wave, then electric field can go back and forth, inducing magnetic field in orthogonal direction. And we normally define the plane of polarization to be the plane of the electric field. That's this cyan color. So in this case, we are talking about, oh, I'm sorry. This is the pink color. I'm sorry. Here's the electric field. So this is the direction of electric field, and that's the plane of polarization. So that's one possibility of this planar polarization of the electromagnetic field, electromagnetic wave. And if you rotate the whole thing by 90 degrees, then the electric field is now pointing in this direct plane, oscillating like this. And that's the case of another linear polarization of the electromagnetic wave. So they correspond to these two vectors. So if you, again, go to the case when momentum vector is pointing in z direction, you can achieve that by setting both polar angle theta and azimuthal angle phi to 0. So only component is then here, and that's the z direction for the momentum. Then epsilon 1 would be 1, 0, 0. So this polarization vector is pointing in x direction. Epsilon 2 would be 0, 1, 0. So polarization vector is now pointing in y direction. So that's a special case. And for generic direction of the momenta given by this polar and azimuthal angles, these are the two independent polarization vectors. So that's how we actually discuss the classical electromagnetic wave. But now we're talking about annihilation and creation operator associated with that particular polarization vector. And then we're talking about annihilation creation operator of a photon of a particular polarization. So that's the idea of this A lambda and A lambda dagger. And then you know already how to construct the Hilbert space out of that. And commutation relation for each polarization is given by, again, the usual commutation relation of annihilation creation operator. And then you have to satisfy that two annihilation and creation operators refers to the same polarization, so that you have this Kronecker delta between two polarization states in this commutation relation. So that's the idea of the linear polarization. And then you can go to also circular polarization next, but let me get back here and see if there are any questions about this situation with the linearly polarized electromagnetic wave and correspondingly linearly polarized photons. Any questions? Is everything okay? Then I believe you have also heard in the classical E&M that this is one possible basis of polarization, but you can also choose the basis of the circular polarization. So this is the picture of the circular polarization. This is the linear one we have looked at on the previous slide. And this is a picture of the circular one. So the plane of the electric field starts to rotate as the wave propagates. And that defines one circular polarization. And you can have another polarization where it goes the other way around. Namely, whether it's clockwise or anti-clockwise is the two possible circular polarizations. And circular polarization has the polarization vector of its own, which is given by just a linear combination of epsilon 1 and epsilon 2 we had for linear polarizations. There's a factor of I in between. And this plus minus sign takes care of clockwise versus anti-clockwise. So what you're doing is just rewrite this basis vector epsilon I, you have two of those, in terms of two other basis vectors, epsilon plus and epsilon minus. So just a change of basis in a two-dimensional linear space. So obviously that's something that can be done. And you change then the sum over two polarization states from 1 and 2 to plus or minus, but expression still looks the same. So this A lambda for A plus is now a linear superposition of A1 and A2. A minus would be the opposite linear combination of A1 and A2, and so on and so forth. So then you have this mode expansion again, where now A is labeled by plus and minus polarizations instead of 1 and 2 polarizations. And that is the way you can define a photon of the circular polarization. So that business is again exactly the same as you have seen for a classical electromagnetic wave. Okay, let me stop here again. Are there any questions about this? So this is sort of, oh, go ahead.
Oh, yeah, I have a quick question. If we're taking the dagger of A, then wouldn't we also be taking the dagger of E or of
that's
epsilon?
Right. Yeah,
and so it would be conjugated?
Yes, thank you for asking the question. And I forgot to do this. So this is the typo. Okay? So I should have put star on this so that I changes to I minus I when I write this out. And I should have done it, but I haven't. And so thank you for pointing out the mistake. I will correct the slides later on. Thank you, Riley.
Okay.
Any other questions? Okay, good. Now we are getting there. So either linear polarization or circular polarization, you have this mode expansion. And once you have a Lagrangian, you can of course define Hamiltonian too. And PQ dot minus Lagrangian is something you need to work out. What we have learned is the Q is A, vector potential, P is A dot. So that will give you A dot squared. And so that is partially canceled by Lagrangian. That's half A dot squared. So the remainder is half A dot squared. So that's this term here. And I just rewrote A dot in terms of the electric field in the absence of the matter fields. And this is just the negative sign of the Lagrangian. So Hamiltonian now we know is E squared plus B squared. And we also know how vector potential is written in terms of creationization operators. So I can plug this mode expansion into the Hamiltonian. And it's kind of complicated. You have this momentum and the polarization, and you also need the spatial integral. But once you are all done with it, what remains in the end is very simple. Because after all, this is also a harmonic oscillator. So for every momentum mode in this cubic box, and for each of the polarization mode, lambda, here's the number operator, A dagger A, that counts the number of photons. And for each photon, you associate the energy h bar omega p, as we talked about, I think 3 slides ago. So h bar omega p is this vector p, absolute value times speed of light. And speed of light comes out because, as you might remember, epsilon naught times mu naught is 1 over speed of light squared. So if you actually carefully work out all these factors on dielectric constant and the permeability, then you find that the factor of speed of light correctly appears here. And then Hamiltonian ends up being this very simple form of independent harmonic oscillator for a photon with a given momentum P and polarization state lambda with energy h bar omega p as expected. And then this is very simple to understand. So now this is the way we can be fully confident that the Maxwell's Lagrangian is just what reduces to a collection of independent harmonic oscillators for each photon mode. Then you know what to do, how to construct Hilbert space. You define the vacuum state, which is annihilated by the annihilation operator for every p and lambda. And then using this vacuum state 0, you act creation operators on it. And that's the way you can define the Fock space. Again, exactly the same way we did for the Schrödinger field in the case of boson. We are talking about canonical commutation relation, not anti-commutation relation. So this is supposed to be a boson. And then therefore the Fock space is given this way. In principle, you can occupy the same state, same momentum and same polarization vector multiple times. So you can put multiple photons into the same state because it's a boson. And here is the Fock space. So now you know what the Hilbert space for this theory is as well. And it turns out that the idea is exactly the same as you have done with the Schrödinger field. So the only complications we had to go through is the fact that you have 3 components and you have this gauge condition. And using the gauge condition, 3 components got reduced to 2 polarization vectors. Then that's how you find the photon of 2 polarization states for every momentum mode. And just a collection of creationization operator then describes the entire electromagnetism coming from this Lagrangian for the Maxwell field. So that's how you quantize the electromagnetic field and indeed fight photons. So this is what you got told many times at the beginning of the quantum mechanics class. You need to study quantum mechanics because we discovered photons. Photons can be emitted from atoms, they can be absorbed by the atoms, they can scatter, they can do Compton scattering, photoelectric effect kicks out the electron from the material, and all these had to do with the photons, but you haven't seen that before. For now, you are equipped with QFT, and by regarding the vector potential as the quantum field, we just went through the same procedure we have done with the non-relativistic Schrödinger field, except for this multi-component thing in gauge invariance. But apart from these little complications, the idea is still exactly the same. And then you find photon in the Hilbert space of this quantum field theory. So this is the idea of how you get photon in quantum physics. Okay, any questions about this? No? Everything clear? Okay, so you have seen this already, but this is the moment to celebrate. You now finally see a photon in quantum physics by quantizing electromagnetic field using canonical quantization condition of the quantum field theory. Okay, by the way, this is a video I took myself when I was just happening to visit in Geneva to go to CERN. That was just accidentally happened to be the day of the summer celebration of the fireworks. So I went down there, I took this video. So I still love watching it. All right, now we know that this A and A dagger are the creation annihilation operators of the photon. But we can now ask the inverse question. So we started out with the vector potential, we quantized it, and got a photon now. But we also know there is a thing called the classical electromagnetic wave. And if there was such a thing, then you can use Wi-Fi to connect to this lecture right now, right? So when you're using Wi-Fi, you have a router that emits the radio wave of 2.4 gigahertz or 5 gigahertz, depending on which mode of the Wi-Fi you're using. And that's a classical electromagnetic wave. And that classical electromagnetic wave reaches your computer and oscillates electrons in an antenna embedded inside your computer. And that creates the electric current. And then the computer would detect that and then decode the signal of this, all these bits of the data out of this radio wave. And that's how you can look at my lecture right now. So there is a thing called the classical electromagnetic wave. And how do we understand that? Now that we have this quantum description of photons. But I believe you can guess the answer already, because we did ask this inverse question before using the Schrödinger field. Schrödinger field, the way we constructed, was supposed to describe particles. But once those particles cool down to very low temperatures, then all the particles start to overlap and start to behave as a classical wave. And that was the Bose-Einstein condensate. And that was the classical wave described by the Schrödinger field. We know, ahead of doing this quantization business, we know the classical field vector potential describes the classical electromagnetic wave. So from the point of view of the quantum field theory, we know what that is. Namely, that's a Bose-Einstein condensate of photons. And to be more specific, we describe the Bose-Einstein condensate using a coherent state. And that's an example of the harmonic oscillator physics we talked about at the very beginning of this class. And that is what you're supposed to use now. Namely, you define a coherent state of photons. So I concentrate on one particular momentum mode P in one particular polarization lambda. And here's the creation operator of the photon for that momentum and that polarization. And just like what we did in BAC, BEC, and also originally in harmonic oscillator, you define the coherent state by acting exponential of the creation operator on the vacuum state. And to make it properly normalized, I have this normalization factor of e to the minus f star f over 2. And you already have worked this out a while ago. It's in one of the homework problems. So we know what this coherent state is. But we still haven't made the precise connection to the electromagnetic wave. So let's do that. Namely, what you're supposed to do is to look at some simple case where momentum we're facing the z direction. I also choose the simple case where polarization vector is purely in the x direction. And just focus on that momentum and polarization for now. And define this coherent state by acting the creation operator for this momentum along the z direction and this polarization vector along the x direction. And x direction of epsilon is there only for the x component of the vector potential. So I don't need to consider y and z component of vector potential anymore. So I just focus on the x component of the vector potential. And using this coherent state, I can compute the expectation value of this vector potential. And we know that a coherent state is a eigenstate of annihilation operator. So this A lambda acting on the coherent state will pull out the eigenvalue F. In the same way, this A lambda dagger acting on a coherent state bra would extract eigenvalue F star. So here, it's easy to compute the expectation value of the vector potential in a coherent state of the photons. Now you see that this indeed has a form of a wave. And especially when you assume F is actually a real number, in general it can be complex, but let's assume it's a real number, then F plus F star adds up to give you cosine PZ over H bar. And that's exactly the form of a wave. And you can also compute the expectation value of A dot by using exactly the same idea. Then this is the opposite linear combination. So this turns out to be sine PZ over H bar. So now you know that this correctly describes a snapshot of the electromagnetic wave at a given instance T. A is cosine, A dot is sine, and they are opposite in phase. And they both oscillates in the X plane, XZ plane, because we are looking at the polarization vector in X direction. And it propagates to the Z direction because the wave factor is cosine PZ over H bar. So that correctly describes a classical wave moving in a positive Z direction. So this is actually the real nature of the classical electromagnetic wave. So whenever you see a classical electromagnetic wave, like this Wi-Fi signal you're using right now, or things like a laser, then you actually secretly be looking at this the coherent state. And once you know what A dot is, you know what the electric field is, which is negative A dot in the Coulomb gauge. And that's something you get immediately just by changing the sign of the expectation value you have already computed. So this really shows that the polarization plane is in XZ plane. Now you also have this expectation value of the X, so you can take the curl of it. The curl of X component is either del Y AX minus del X AY, but Y derivative vanishes because the dependence on coordinate is only Z dependence here, so you can forget about it. Another possibility is del Z AX minus del X AZ, and AZ vanishes in our case. So this is the only thing you need to compute. So del Z of AX is what gives you BY, the electric magnetic field in Y direction. And that's something you can also immediately work out from this expression over here. And they are in the same phase. Both of them are sine PZ over H bar. And that's what you would expect for a classical electromagnetic field. And also that the plane of electric field, the plane of the magnetic field are indeed orthogonal to each other. And both of them are orthogonal to the direction of the propagation. So that's exactly what this picture says about the classical electromagnetic wave. So what you observe here is that by defining the coherent state of the photon for a given momentum and given polarization, you can get expectation values of A and A dot for this vector potential. And knowing that, you can compute the expectation value of electric field and magnetic field. And indeed, the form of this expectation value of electric field and magnetic field correctly describes the propagating classical electromagnetic wave. You have the direction of propagation, you have orthogonal direction of the electric field, you have yet another orthogonal direction of the magnetic field, and electric and magnetic field oscillates as a function of Z in the same phase because both of them are sine PZ over H bar, and that's exactly what you would expect for the electromagnetic field in classical E&M. So now you understand the classical electromagnetic wave, the Wi-Fi signal, or things like laser are actually coherent states of photons. So whenever you see this laser pointer, you always should think, aha, there is a coherent state. And that's the way we understand the classical electromagnetic wave now using this language of the photon. So the true nature of the classical electromagnetic wave turned out to be the Bose-Einstein condensate of photon. We normally don't use this word. We say this is the coherent state of the photons. And that's exactly what a classical electromagnetic wave is. Again, just to emphasize once again that expectation value of field can exist only when your state has a linear combination of states with different number of particles in it. Because A of x either decreases or increases the number of photons. If the state is a number state, then number n would go to n minus 1 or n plus 1, so the expectation value vanishes. So it is essential, in order to have an expectation value of the field, you need to use a state that has a linear superposition of states with different number of particles in it, coherent state being one prime example of that. And so you do need linear superposition of states with different number of particles. And I emphasized this again some time ago, that kind of linear superposition is you cannot talk about in the standard quantum mechanics formulation, because quantum mechanics uses wave function, and wave function specifies how many particles there are ahead of the time before writing the wave function. And therefore, you cannot take linear superposition of states with different number of particles. But in QFT, you have this huge Hilbert space which contains states with no particles, one particle, two particles, three particles, ... And you can take linear superposition of states with different number of particles this way. And coherent state is one such an example. And only in a formulation where you can talk about this kind of weird linear superposition, you can hope to get non-zero expectation value of the field operator, which can correctly describe a classical wave, and hence the coherent state of photons. So that's how everything sort of comes back in circle. So we started doing quantum field theory by thinking about particles in our mind and trying to think of putting particles on different sites on one-dimensional lattice. We wrote down the Lagrangian Hamiltonian. We took the continuum limit to come up with the Schrödinger field theory. So we quantized particles to get the Schrödinger field theory, and classical Schrödinger field theory turned out to be the Bose-Einstein condensate of atoms. In the case of electromagnetism, we are actually doing it in the opposite direction. We start with the classical electromagnetism written in terms of vector potential. We already knew Lagrangian for it from Maxwell's theory. And we quantized it and found the photons from it. But from the photons, that's the individual particles, we can go back to the classical theory in the same way that we went back from the Schrödinger particle to Schrödinger wave, which described the Bose-Einstein condensate. In the same way, we can go back from the photon to classical electromagnetic wave, which is the coherent state of the photons. So that's the way everything is actually now treated on equal footing. In quantum field theory, your variable is a field that describes a classical wave. When you quantize it, you find particles. When you take a classical limit, you get a classical wave again. So that's a particle wave duality. But rather than taking starting point from particles, that's what you did in quantum mechanics, we take the starting point to be the field, which describes a wave. And now we're using the same formulation, both for matter particles, using Schrödinger field, and the photon, namely electromagnetic field, and starting with the same starting point of a field. You quantize it, get the particles out, but altogether, you describe this funny, bizarre system, which is particle and wave at the same time. Quantum system is neither completely classical wave, nor completely quantum particles. It's somewhere in between, but you do get precisely that kind of object by quantizing the field. And that's how QFT is supposed to work on general grounds. So Schrödinger field theory was in some sense a warm-up example for the purpose of getting photons out of classical E and M, if you look at this way. Of course, Schrödinger field by itself was useful because we needed it to describe superfluidity, superconductivity, Bose-Einstein condensate. So that was useful anyway. But now you see the concept of quantizing the field now applies much more generally. And we apply this in the case of the vector potential in electromagnetism. And you correctly got the photons. And using photons, you can correctly describe the classical electromagnetic wave using the coherent state of the photons. And everything comes in full circle and everything works out in a fully consistent fashion. And that's general idea of QFT. Okay, so I said a lot, so let me stop here, and I'm sure you got some questions. Chirag, are you trying to ask questions?
Oh yeah, I had a question.
Go ahead.
So with the BECs, we saw that to get the coherent state, you require like some temperature conditions. So in the case of photons, are there any conditions that like specify when you can get a coherent state?
Yeah. So in the case of the Bose-Einstein condensate, we talked about this really cold system at nanokelvin temperature, where the matter particles really start to collective like a wave. And we talked of fringe patterns, so on and so forth. But once you start to heat the system up, then the classical wave now breaks up into individual particles. So that's the behavior we have seen in the case of the Schrödinger field. And idea is same here. So laser is, in some sense, zero temperature photons, and all the photons are now condensed in one particular momentum mode and one particular polarization, in the same way that in the case of BEC, you talked about zero momentum mode, in which macroscopic number of particles condensed. So it's the same idea. But we can't talk about electromagnetic field at rest, because this is relativity now. Photon has to keep traveling with speed of light. So there's no condensation or zero momentum state. That's something we cannot talk about. So instead, we talked about the photons, macroscopic number of photons condensed in a particular momentum state. But you can see it's the same idea. So laser is, in some sense, zero temperature Bose-Einstein condensate of photons. Then you ask the question, what happens if you heat that up? And you know the answer already. If you heat the system up, then you are talking about black body radiation. Black body radiation is you have a hot surface, and you observe individual photons coming out from it. It's not a coherent electromagnetic wave. It's an individual photons coming boom, 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 boom. And you observe that, and you find this black body spectrum of the photons. And black body spectrum is something you can understand by thermodynamics of individual particles that carries the energy h bar omega, and that's the discovery by Planck, right? So he was grappling with this question, why does the black body spectrum look like the way it does, especially why does it damp exponentially towards the higher frequency? And that is now understood because of the Boltzmann suppression for high energy photons. When photon energy is higher than kT, you see this Boltzmann suppression, and that's how you understand this entire black body spectrum. And that's something you are seeing right in front of your eyes. If you heat up the system, then classical electromagnetic wave would break up into individual photons. They no longer occupy the same momentum mode anymore. And they're still distributed according to a formula, which is nothing but the Planck law of radiation, because individual photon carries energy, definite energy of h bar omega. And that's how you can understand the black body radiation as the collection of individual photons, not the classical electromagnetic wave. So does that answer your question, Chirag?
Yeah, thank you.
Okay, good. So the next time you look at stove and you turn the gas on and see the glow of light, you should think about, okay, this is the individual photons coming to my eyes, and because that's exactly what it is. Any other questions? By the way, if I understand it correctly, our retina is an excellent single photon counter. It actually does detect individual photons. It's not detecting electromagnetic wave. So if they want for quantum mechanics, you can even see things. The optical photons are not coherent with each other. They come in as individual photons. It's not a classical electromagnetic wave. And your retina counts the number of photons that causes electrical current in your retina. And that electrical signal goes through your nerve cell all the way into the brain. And that's what you think you are seeing something. And that's based on these individual photons. So that's something useful to remember. All right, any further questions? Is it good? Okay. And I already finished talking about this slide. So the expectation value of the electric magnetic fields in the coherent state really does correctly describe the classical electromagnetic wave. And that's what I already talked about. Any questions about this little algebra? I will be asking you to do this in the homework. Everything okay? All right. So now what we can do is to really talk about these quantum phenomena you were told about at the beginning of quantum mechanics class. So in that case, you were talking about things like, for example, the hydrogen atom. So you have a point particle with this Lagrangian, and Lagrangian has the kinetic energy term, which contains this vector potential in it. And so this Lagrangian, from the point of view of quantum mechanics, I'm sure looked like this is what you would use when you have a point particle moving in the presence of a classical vector potential, like static magnetic field. And indeed, you can use it that way. Then you quantize this Hamiltonian, find the Landau levels of electrons moving in a static magnetic field. So that's totally fine. But now you realize that this Hamiltonian can do something more than that. It contains a vector potential in it. And vector potential is now written in terms of creation-annihilation operator of a photon. And therefore, this Hamiltonian, which you have seen many times in 137, can create or annihilate photons. That's the use of this Hamiltonian you probably have not seen in 137 because the electromagnetic field in this was classical. But now you know what to do with it. Once you have this vector potential in it, you write this out using creation and annihilation operator of photons. Then using this Hamiltonian, you can describe a process that can create a photon or annihilate a photon. In other words, you can describe a process that emits, namely creating a photon, or absorbs, namely annihilating the photon. So when you want to talk about emission of a photon from an excited state of an atom, this Hamiltonian can already describe that because it can create a photon. If you want to describe a process where you send in a photon that gets absorbed by an atom to go up to an excited state, you can describe this with the Hamiltonian too, because this Hamiltonian contains an annihilation operator of a photon. So this familiar Hamiltonian, now you know, can do a lot more. And this is what you can use to indeed describe emission and absorption of photon. So you used to use this vector potential as an external classical field in 137, but now you know A is a quantum field which can create or annihilate a photon. So you use the same Hamiltonian to describe a time evolution of a state where number of photons can change. Namely, it can create a photon as time proceeds. That's an emission process. Or it can annihilate a photon as time proceeds. That's an absorption process. So creation of the photon can happen if the atom is in an excited state and it goes down to a ground state of the atom by emitting a photon. That's a de-excitation that leads to an emission and therefore creation of a photon. And one prime example of this is that you have a hydrogen atom where electron is orbiting in a 2p orbital. And that's an excited state. Then it can decay down to the ground state of 1s by emitting a photon. And that's how you get told that the photon you see from atomic system comes in discrete spectra. but you haven't heard how exactly you actually compute that in quantum mechanics. But now you do. Using this Hamiltonian, which you knew all along, using this Hamiltonian, you can now talk about this time evolution of the state in 2p, transforming to a state of oneness state of atom plus one photon of definite energy. And that's how now we would like to work out using this Hamiltonian to describe that process. And of course, 2p to oneness is only one example of such a emission process of photon. You can think about all the other kinds of de-excitation process that leads to Lyman series, Balmer series, Paschen series, and so on, as you learned in quantum mechanics class. And you can apply the same argument to any other transitions as you like. So what I would like to do next is get into this question, how we actually compute this process of the excitation of atoms using this familiar Hamiltonian, P minus EA squared over 2m. We don't need scalar potential for that purpose. And then work out its consequence. Oh, I'm sorry, I misspoke. You do need, of course, scalar potential for the Coulomb potential coming from the nucleus. So you do need that, but it doesn't contain a photon, as you saw, because the Coulomb potential doesn't contain the vector potential in it. Photon is contained only in here as a part of E minus EA. So I misspoke. Phi is there, but it's just the Coulomb potential of the atom. So you have this P minus EA squared over 2m, which contains the photon creation and addition operators in it, plus Coulomb potential. That's the Hamiltonian for the electron inside the atom. And using this Hamiltonian, we can now go ahead and compute this process of 2p decaying to oneness by emitting a photon of definite energy. So that's what we like to do in the next slide using Fermi's golden rule. Anyway, let me stop here again. I spoke a lot, so I bet there are some questions. Is everything clear where we're heading to? So we started with the classical EM. We quantized classical EM to find photons in it. And we found the Fock space of the photons. But then we go back to this familiar example of the point particle in electromagnetic field. But now we have a new interpretation of this Hamiltonian. Rather than regarding this as a Hamiltonian of a point particle like electron in the presence of classical electromagnetic field, like constant magnetic field or Coulomb field. That's the way we use this Hamiltonian. But instead, we can use this Hamiltonian to actually create or annihilate a photon because the vector potential, now we know, contains creation annihilation operator of a photon. So using this Hamiltonian and combining that with the Fermi's golden rule, then we can now compute the decay of the 2p state into oneness state by emitting a photon. And you might find it a little odd that, well, we studied quantum field theory for matter particles already. Why are we talking about a single particle Hamiltonian for now? Well, it's just to avoid too much complications. In the end, we both treat the matter particles like electron and electromagnetic field or photon, both of them based on a field on equal footing. But before getting to this full theory called the quantum electrodynamics, we go by steps. So now we are using a field for photon, but we are now using point particle for the electron and try to use this as a practical application now. But we can then move into also using point particles using field later on. And that's exactly you have to do, it turns out, when you go to relativity by using what is called the Dirac field and Dirac equation. So we are not getting there yet. We are treating electron as a non-relativistic point particle, no field, no relativity, just to simplify discussions here. But using that description of non-relativistic point particle electron, but we still need to talk about photons because after all, photon is emitted, but we know how to do that because vector potential is in here that contains creation operator of the photon. So this is actually pretty much all you need for this particular purpose. And that's why I'm using the simpler description without using Schrodinger field for now and talk about this process of emission of the photon. Just to be clear about this. Any questions? Are you sure? I hope you guys are not getting lost. Maybe one of you can give me thumbs up if everything's okay. Okay, I see thumbs up. All right, thank you. So let's use that now. And let me just review Fermi's golden rule, which I hope you have seen in 137b, I think. So the idea is that you split Hamiltonian into two pieces, and you use basically perturbation theory. So H0 is the main Hamiltonian, and you quantize this correctly and exactly, and you know the states and energy levels. You treat delta H as a perturbation to the system, so you regard this delta H to be something small for the purpose of discussion. And using the split of the Hamiltonian, the first thing you do is look at the exact eigenstates of H0 and identify initial and final states as eigenstates of H0. So in the case of the atom, the initial state is a 2p state of hydrogen atom, and H0 is just the kinetic energy term for the electron plus Coulomb potential. That's the H0. You know the eigenvalues and you know the eigenstates exactly. You have solved this problem for the hydrogen atom. For the final state, that's also an eigenstate of H0. So H0 is now an eigenstate of oneness state. But in addition to it, H0 should also contain the free photons as well as a collection of the harmonic oscillators, so that H0 eigenstate can also contain a single photon that got emitted from the decay of the 2p state. So now you know what I mean by H0. H0 contains p squared over 2m for the electron, plus Coulomb potential minus e squared of 4 epsilon naught r, plus the sum over the photon harmonic oscillators Hamiltonian h bar omega a dagger a for every p and every lambda, and that's H0. And then transition can be caused by this perturbation to the system, delta H. And the rate of the transition is defined to be the probability that transition happens per unit time. And that is computed by this Fermi's golden rule, namely that if you have an initial state I, that's an eigenstate of H0. F, that's also an eigenstate of H0. You compute this matrix element of this perturbation between the initial state and final state. And once you compute this matrix element, you square this, divided by H bar, and multiply with a delta function of energy conservation to obtain the probability per unit time, and that's the rate of transition. And that's the famous Fermi's golden rule. And you derive this from time-dependent perturbation theory, and we actually end up re-deriving it later. So if you have forgotten about this, don't worry about it for now. We will derive it later on, because it turns out that later on, we also need to extend this Fermi's golden rule to higher orders in delta H, it turns out. So we will re-derive it. So if you don't think you remember this derivation, that's totally okay. We'll come back and talk about that. But there are two important points. One is that once you know what the initial and final states is, all you need to do is to compute this matrix element of a single operator delta H. Then you know this piece here. And second important piece of information is that this automatically requires energy conservation. Namely that when 2p state decays to oneness state, this delta function is what requires that energy of the photon is precisely the energy difference between 2p and oneness states, and hence the discrete spectra of photons. And that is now a consequence of the Fermi's golden rule. So it didn't need to go through some hand-wavy argument. Well, energy is conserved, the states are quantized, that's why photon energy is quantized. Now you see this is the mathematical consequence of the quantum field theory. And for our purpose, H for the electron is p minus EA squared over 2m plus E phi, as we already talked about. And H0 contains only this p squared piece in it, to describe the energy eigenstates of the hydrogen atom. And the rest is delta H. So only thing I need to do is to expand P minus Cj squared in terms of P squared, that's part of H naught. And then across from P dot A dot P, and A squared P's. And all these are part of delta H. So this yellow is H naught up here. And this cyan is delta H up there. And in addition, as I said already, I also need to add the Hamiltonian for free photons on top of it to full define H naught at the end of the day, which I did not write on this slide. But I hope the idea is clear. All we are doing is perturbation theory. And perturbation theory is a power series expansion in fine structure constant, or E, it turns out. So electric charge is a small number. And the power series expansion then has this piece linear in E and quadratic in E, and that's delta H. And using this delta H, all we need to do is to compute this matrix element between 2p state and 1s state, then you're done. Then you have now tool to compute the decay of an excited state of an atom by emitting a photon. So the emission of the photon is now something you can just go ahead and work it out yourself. Nothing is mysterious now. All you need to do is compute this matrix element. But now that you have not done this before, computing this matrix element is a little bit technical. So I'm gonna spend a few slides next to show you how you compute this matrix element. But don't be bothered by technical details for now. I hope you get this big picture. So now that you have the Hamiltonian, which has this electromagnetic field in it, you expand this in a spirit of perturbation theory. This is a zeroth order Hamiltonian H naught. This is the perturbation Hamiltonian delta H. There's no ambiguity here. This is just a power series expansion. But the point is that A in this expansion contains creationization operator of the photons. And using this thing in a cyan as delta H in Fermi's golden rule, you are ready now to compute the rate of the process where 2p state I decays into 1s state plus a single photon, and photon is created precisely by a creation operator inside this field operator A. And so that's the big picture. Nothing is complicated. Actual algebra is a little complicated, but I hope you don't get lost by the algebra. The big picture is really just that. Perturbation theory, Fermi's golden rule, and creationization operator. You all know this, and you just go ahead and use it, and that's it. Okay, any questions about this? Here, somebody should ask questions.
Oh, I have a question.
Go ahead, Riley.
Are we still implementing the Coulomb gauge?
Yes.
And it looks like to me that the P dot A would go to 0 because A has the polarization vectors in it, and P dot the polarization vectors is 0.
Yeah, that's an excellent question. It turns out that it doesn't vanish because this P operator is the momentum of the electron, which can also act on the right, which is this I initial state, let's say 2p. So P, if P is acting on A only, then you're completely right, that gives you divergence of A that vanishes. But P also acts on the state on the right, which is this initial state I, and that's the piece exactly you need for the purpose of computing how 2s state can transition to 1s state. So that's an excellent question. So as a matter of fact, because P acting on A gives you 0 by Coulomb gauge condition, I don't need to worry about the order of P and A, it turns out. So P dot A and A dot P are the same. P is acting on the initial state rather than on A anyway. So I can just combine them together with a factor of 2. So that's a simplification I get thanks to the fact that we are using the Coulomb gauge. So P dot A by itself doesn't vanish, no, but Coulomb gauge at least helps us because you can combine these two terms just with a factor of 2, and P still acts on the state of your interest, and that's exactly how 2P can decay into 1s. Okay, I hope that answers the question, Riley.
Yeah, that does. Good. Thank you.
Thank you for the question. Anything else? So in some sense, we are now approaching a climax, right? So this is the process you were told to study in quantum mechanics class, which you were cheated, and you've never seen the answer to that. But now you do see the answer to this question. So now we are approaching this other climax here. Okay, so decay rate. We have delta H. We know what I is. We know what F is. We got everything at our disposal. And as Riley just said, PA commutator gives you derivative acting on A, which is nothing but the divergence. Therefore, that vanishes in the Coulomb gauge. Namely that I can fully interchange the order of P and A thanks to the fact that we are in Coulomb gauge. So the first two terms turn out to be the same with a factor of 2. And when you compute this transition matrix element from 2p state to oneness state in single photon, and both of them are eigenstates of H0. Remember, H0 contains the Hamiltonian for the electron and the hydrogen atom plus the Hamiltonian for the free photons. And therefore, this photon state is part of the H0 eigenstates. And then you stick in delta H in between. And then you realize that you can forget about this A squared piece because A squared piece has either 2 annihilation operators, and that decreases the number of photons by 2, or 2 creation operators that would increase the number of photons by 2, or their cross term where you annihilate and create, or create and annihilate, number of photons doesn't change. But situation we are interested in is a situation where number of photons does change from 0 to 1. So A squared doesn't contribute. So problem is now even simpler. So the only pieces you need to consider are this A dot P inside this delta H. And you use this mode expansion of vector potential. And then the vector potential has a matrix element going from vacuum because a 2p state of electron doesn't have a photon in it. So as far as the photon is concerned, that's a vacuum state. And for the final state, again, as far as the photon is concerned, you're just talking about this one photon state. This matrix element is just given by this creation operator over here. And for some reason, here I was careful to put star, and here I wasn't careful. I don't know why, but anyway, so I should put star in here. So if you compute this matrix element, photon part is just simple. It's the same thing as a harmonic oscillator going from the ground state, the first excited state, using creation operator. So 0, A dagger, 1, it's just 1. Then I'm just writing out the rest. Epsilon, star, and this square root factor, and this exponential factor. So this is the matrix element. And because when you act A, is expanded in P momenta, but your final state has definite momentum Q, this matrix element is non-zero only when mode expansion P has the same momentum as the final state Q. So I already inserted Q everywhere where it used to be written P, which means I should have also changed this omega P to omega Q, which I did forget, apparently. I'm sorry about that. So this is supposed to be omega Q, epsilon of Q, and e to the minus IQ dot x of h bar, where Q is the momentum of the final state photon. So photon part is something you can work out in single line. You already got that. And what remains is really this P over M coming from the rest of the delta H. So the matrix element you need in the end looks like this. So this epsilon star, I wrote over here. And this square root factor, I've written it over here. But this matrix element has dependence on X. And this X is where electron is, right? Because this A is part of the Hamiltonian for the electron. So A depends on X, but that X is a position operator of the electron because we're using the particle description of electron rather than the field theory description of it. So A over X, where X is an operator X. So if I want to emphasize on this, A is the field operator, which is a function of position operator X. is an operator of operator, but it's true. So X inside the vector potential is the position operator of the electron. So there is X. So this e to the minus IQ X factor still has to be kept between the initial TP2 state and final 1s state as a part of the matrix element. And P, which is staying Hamiltonian, still stays inside. So everything now boils down to just the following technical question. Go ahead and compute the matrix element of this operator for an electron between 2p and 1s state. So that's it. Once you're done with that computation, then you know what the decay rate of 2p state is by emitting a photon. But it turns out that that is the part which is the messiest. 2p is given by this Lagrangian polynomial times the spherical harmonics. 1s state is also Lagrangian polynomial times spherical harmonics. You need to put that in here and do spatial integral to compute the matrix element. And that's the part that is the most technical about this. So it turns out the field theory part is rather trivial. It's actually the quantum mechanics part that is the most complicated, but we have to go ahead and do that to compute the decay rate, it turns out. Okay, let me stop here. I'm sure there's some questions before I delve into this calculation of the matrix element. Any questions? In particular, that vector potential is an operator of operator might sound a little surprising, but given the fact that this vector potential is evaluated where electron is, that's where electron feels the vector potential. It's a function of the position of electron, and position of electron turns out to be an operator. So this is an operator of operator for a good reason. No questions? Okay, so then let me just sketch how this calculation would go, because I don't think I have enough time left to go through step by step, but at least you get an idea what's coming. And that's something we're going to discuss next week. So now we look at this matrix element here from 2p state, initial state, 1s state plus a photon as the final state. We know what delta H is for the perturbation, and then we know the expression for it already. So we try to go ahead and compute this matrix element in quantum mechanics of the hydrogen atom. So that's all that remains to be done. So let's keep this matrix element over here, and we try to compute it. But we can start simplifying it. If you look at this expression Q dot X, Q is supposed to be the momentum of the final state photon, right? And that photon has an energy of 2p minus 1s energy. And for a photon, then momentum is energy minus over c, speed of light. So this is the momentum of the photon. On the other hand, X is an operator, but on dimensional grounds, the dimensional sort of distance scale that comes into any calculation of the hydrogen atom system would be at least of the order of the Bohr radius. So let me just estimate how big that may be. And you just plug in the energy of the 2p and 1s states. Here's the Bohr radius. It turns out that there's a very useful way of writing energy levels of the hydrogen atom like this. mc squared, of course, has the dimension of energy. Alpha is dimensionless. And energy levels turns out to be written as negative for bound states, alpha squared times mc squared over 2n squared. This is the same expression you have seen in quantum mechanics class, but I just rewrote it using fine structure constant. And Bohr radius can also be written using fine structure constant. It turns out to be h bar over alpha times the mass of electron and speed of light. Again, this is the same formula you know, I just rewrote it using the fine structure constant. But the reason why writing it this way is useful is because this combination Q dot X, you can see immediately that's actually order alpha, which you know is a small number, 1 over 137, hence physics 137 for quantum mechanics. So this is a small number, and Q dot X is an exponent. So if I expand this in a Fourier series, it starts with 1 as a leading piece, then comes Q dot X, which is suppressed by alpha, Q dot X squared, that's further suppressed by alpha squared and so on. So again, in the spirit of perturbation theory, I only look at the leading term, which turns out to be 1 from this exponential, namely that I can forget about this exponential at all. So the only thing you need is to compute the matrix element of P between 2p state and 1s state. So that's why you need to compute now. And that actually turns out to be computed easier by remembering that P over M can be written as a commutator of X and H naught, where H naught, as we discussed, is a Hamiltonian in a hydrogen atom. And we go through this more slowly next week, so don't worry about details. But then this H naught is acting on 2p and 1s states, then you get these energy eigenvalues. So that further simplifies the calculation to the matrix element of X instead of P. Then I can just write this out in position space. Everything is now X. I don't need to have any derivatives on it. And then this is just simply boils down to the integral over X using explicit form of the wave functions of 2p and 1s state. And because E times X is nothing but electric dipole moment, this is called a dipole transition because of that. So it now reduces the computation of this off-diagonal matrix element of the electric dipole operator. And again, I go through this more slowly next time, but this is something you can just go ahead and compute. So I ignore this exponential factor. This is now a matrix element of P operator, but now we discover that this reduces now in terms of matrix element of X operator, as we just talked about. And what you need to compute is this one. And you know the wave functions of 2p state over here, Lagrangian polynomial times spherical harmonics. This is the wave function of 1s state, also Lagrangian polynomial times the spherical harmonics. And all you need to do is to write this, and this Ex is our cosine theta, and you integrate over the 3 dimension, and that just comes out to be a number which is proportional to the ball radius A. So this is cumbersome, but nonetheless is straightforward. And once you know this, then you dot this together with this polarization vector, where I actually correctly chose the axis so that only one polarization state contributes for simplicity. Then the decay rate is now computed like this. And I used the delta function to actually perform the integral over Q so that I don't have dq here anymore. And then this is again just an integral over the solid angle in which direction photon is emitted, always with a fixed momentum because of fixed energy of the photon. And this solid angle integral is kind of trivial. You just integrate sine squared, and hence end result comes out. And end result is written this way. Alpha to the 5th times mc squared is quite suppressed by 5th power alpha. And it's a fairly small number. But small in this case, in atomic system, is still 10 to the 8th if you use the unit of 1 per second. But this is actually considered to be small in the world of atoms, where the time scale is dictated by the orbital motion of the electron. And compared to that, this is actually very small. And you can do the measurement of the hydrogen decay. You create an excited state in a laboratory, and you measure the exponential decay law by observing many, many 2p states as a function of time. And then you can extract this exponent that turns out to be this number. And you can see they agree very well. And we did not compute higher order powers in alpha. So this is a level of agreement you can expect, not better than that. And they perfectly agree within the spirit of perturbation theory. So that is something you compare with this exponential decay law you measure in the laboratory. So this exponent here, tau, is the lifetime of 2p state. In lifetime of the 2p state is inverse of this decay rate for obvious reasons. And that's indeed this inverse of this one, 1.6 nanosecond. So that's how you can compute the lifetime of the 2p state now. And that's the steps we'd like to go over in a little more slowly so that you can follow every step on next Monday. But anyway, I hope you see the big picture on how we can use this to compute this process, which you could never do in quantum mechanics, but now you can do in rather straightforward fashion now that you know QFT. Okay, I'm sorry I went over time, And I lost quite a few people by now, but anyway, are there any questions? Okay, good. So I do post the homework problem later on. So have a good weekend.
Thanks, Professor.
Have a good weekend.
Bye.